Good morning, everyone. I'm Yican from Peking University, and I will talk about parameterized inapproximability hypothesis under ETH. This is the joint work with my great collaborators Venkat, Binkai, Shendi, and Kevin. Okay, let's start. So before this talk, this seminar, we have introduced many great approaches in parameterized inapproximability theory. For example, we have threshold graph composition, we have distributed PCP framework, we have parallel decodable and testable code, we have sequence sets, we also have other combinatorial approaches. However, it is natural to ask if there is a unified and powerful machinery for parameterized inapproximability. In other words, could we have a parameterized PCP theorem? So if we want to learn PCP theorem, we need to first introduce a constraint satisfaction problem. In particular, we focus on the RT2 case, which we use 2CSP for short. So in the 2CSP, imagine there is a graph. For example, the graph in the left side, we have 4 vertices, which we call variables. We also have 4 edges, which we call constraints. And for every constraint, there is a relation assigned to this constraint. There is also alpha by sigma, and we want to assign each variable a value in the sigma. We say a constraint uv is satisfied if sigma u and sigma v belongs to the relation pi uv. And our goal is to find an assignment that maximizes the fraction of the constraint to be satisfied. And its formal definition is defined below. As a concrete example, we consider 3-color, which is just 2 CSP problems with alpha beta 0, 1, 2, and the constraint relation is just this equality. And this proves that 2 CSP is essentially NP-hard. So what about approximating 2 CSP? And this is exactly the PCP theorem targets on. The classic PCP theorem just says that assume P does not equal to NP, and for every constant alphabet size, there is no polynomial time algorithm that can approximate 2 CSP with constant ratio. And it has a wide applications to inapproximability in NP world. For example, max click, stack cover, max coverage, TSP, something like this. In the parameterized world, we still have a parameterized PCP theorem, which is introduced by LRSC20. So the main difference is that in the parameterized world, for example, we let the number of variables to be k and the alphabet size to be n, and we assume that the number of variables is much smaller than the alphabet size. This is used to capture some canonical parameterized problems such as k-click, where we need to find a click of size k in a graph of size n. For k-click problem, we can reformulate it in using 2CSP. Just we have k variables, and each variable is just a vertex in G, and the constraint between them is saying that every two variables is adjacent in the graph. So parameterized 2CSP is W1 hard, and assume W1 does not equal to FPT. It has no FPT algorithm. On the other side, it has a very trivial n to the k algorithm. We just use some brute force, enumerate every assignment, and try if it is a solution. So the parameterized PCP theorem, which is also known as parameterized inapproximability hypothesis, PIH for short, is saying that there's no FPT algorithm that we can approximate 2 CSP with constant ratio. We also have a tight version saying that we need to rule out every algorithm with running time fk times n to the little ok. Parameterized PCP theorem also has a wide application in the parameterized world. For example, the k max coverage, k exact cover, also some geometric problems such as k median and k means, and some coding problems like KNCP and KMDP. Compared with the classic PCP theorem, where it focuses on the constant alphabet size and rule out polynomial time algorithm. The parameterized PCP assumes is in the setting of arbitrarily large alphabet and focus on ruling out FPT time algorithms. We will focus on how to prove PIH. So the big prize will be establish PIH under the weakest assumption W1 does not equal to FPT, but is still open, and we don't know how to do that. And in this talk, we will based on some weaker assumption ETH and prove PIH is true under ETH, and we also will give a quick look at some quantitative improvements. So what is ETH? Though it has been introduced for many times in this talk, but I will still do a quick recall. It says that 3-set requires 2 to the omega n runtime, and we can use sparsification lemma, assume that the number of clauses is linear with respect to the number of variables. We can also use some Tovey's reduction, saying that every variable appears in at most 4 clauses. To prove PIH under ETH, we need to reduce the 3-set formula phi to a parameterized 2CSP instance, where if phi is satisfiable, then the instance psi is also satisfiable. If phi is not satisfiable, then every assignment to the 2CSP instance will violate at least 0.01 fraction of constants. And it is a parameterized reduction, so we need to ensure that the number of the variables in psi has only k variables, and the alphabet size is 2 to the little n. This is because we need to fit in the ETH runtime. Our overall framework is like we first identify a ETH-hard problem, which we call vector-valued CSP. And we first reduce 3-set to this ETH-hard problem, and we then use PCP verifiers to produce the gap. So let's just look at the vector value CSP. So vector value CSP is a special parameterized 2CSP problem where the alphabet is f to the d. It is exactly the d-dimensional vector space over the finite field f. In our reduction, we use the constant size f. And for every constant is either parallel or linear. And for parallel constant, we mean that there is a same subconstant that is set over that is applied on every coordinates, which means that for every coordinate, the sigma ui and sigma vi belongs to the subconstant. And for linear constant, it's just saying that sigma u is exactly multiplying a matrix M to the sigma v. Yeah. Below, I will going to talk about why we need to define such kind of CSP and give some intuitions here. So this is essentially inspired by by some previous work on inapproximability of k-clique, which says that we can, from this previous work, we can say that if every constant is parallel, then we can use some parallel testable and decodable codes to produce some gap instances. However, the bad news is that if every constant is parallel, the problem becomes a FPT problem. It can never be ETH-hard because in this CSP instance can be partitioned into layers, and each layer is just a sub-CSP with only k variables and alphabet size constant. And different layers are independent, and they are actually identical instances because it is the same constant sets to every coordinate. So in this case, we can solve this CSP layer by layer, and it's a very efficient FPT algorithm. So we just start playing with the 3CNF instance. I mean, if every constant is parallel, then it is good. But it is impossible. So we try to make more constants to be parallel and see what is the remaining constants here. So this is just like playing a magic cube and iteratively do transformations on 3 set and see what we can get in the end. And we do this, and we find that all remaining constants are just linear. So linear constants is also very good because it is a good fit for the Hadamard code, and we just generalize the classic Hadamard code-based PCP, and we can also create a gap. But vector value CSP is a mixture of the parallel constants and linear constants. So we have reductions for each type of constant. We just combine them into one reduction, and then we prove PIH. So first, we will go into some details on how to reduce the 3-set formula to vector value CSP. We first do parameterization. Assume there is a 3CNF formula phi with m clauses and n variables. We apply the constraint variable check to the instance, and we group the clauses and the variables into k groups. And each clause group has m over k clauses, and each variable group has n over k variables. We expect that the clause group will take the value a vector with dimension m over k, and the variable will take a value, a partial assignment, which is a vector of n over k. We also set constraints between these groups. The constraints is just saying that the partial assignment to the clauses is valid, and the partial assignment to the clause is consistent with the partial assignment to the variables. Yeah. But at this time, we just get a parameterized 2 CSP, but the constraint is neither parallel nor linear. It's very complex. Our basic idea is just we have a deeper analysis to these constraints and try to decompose it into simpler forms until we get the vector value CSP. So we first, for example, we analyze the constraints between C1 and V1, and the same procedure will apply to other constraints. Our first observation is that the internal constraint between C1 and V1 can be categorized by 2 numbers, I and B. It's just say that the ith variable in the clause is exactly the jth variable or the negation of jth variable. For example, the constraint between C1 and V1, there is only 2 different predicates, and yeah. So there is at most 6 different subpredicates here. So we can split it into 6 variables, and each variable is for a type of subpredicate, and we add equality constraints between them. So this is just a equivalence transformation. We split into more variables, set consistency between them, and decompose the and spread the constraint between these variables. So now the constraint between a closed group and a variable group only have a unique type of subpredicates, and we focus on one constraint here. By further analysis, we can find that this graph it has left degree at most 3 and the right degree at most 4. The left degree is at most 3 because every clause has at most 3 variables, and the right degree at most 4 is because every variable appears in at most 4 clauses. This is by Tovey's reduction. So we can do further split, and so that the internal constraints and add more equality constraints between them, and we can make the internal constraint to be in a matching form. And then finally, we just add some auxiliary variables, and we can split the constraint into a parallel constraint and a linear constraint. For example, for these 2 variables, we add an auxiliary variable. This variable because the left alphabet has dimension 4 and the right alphabet has dimension 2, we need to pad them into the same dimension, and we also need to add a projection constraint saying that the projection of the auxiliary variable is exactly what we want. Yeah. So finally, we can successfully reduce 3 CNF formula to a vector valued CSP. And then I will talk about how to create gaps from a vector valued CSP to its gap version. We need to use the PCP verifier. So I will introduce what is PCP verifier here. So given the CSP instance, and we want to verify whether assignment is exactly the solution of this instance satisfies every constraint. So the simple verifier is just, okay, we have an assignment here. We just enumerate every constraint and see it is satisfied or not. The good thing is that this verifier is always correct. It always accepts the solution and rejects non-solution. But the bad thing is that it needs to read the entire solution sigma. The PCP verifier does something different. It first sample a randomness R and make only Q queries on the. It not only it takes on input the solution sigma, but also some auxiliary proof pi. And then it first do some randomness and make only a constant number of queries on sigma and pi based on the randomness, and then decides to accept or reject based on the query result. So for every CSP solution, we need to make sure that for every CSP solution, there always exists auxiliary proof that accepts with probability 1. And for every non-solution, we need to make sure that the verifier accepts with probability 0.99, no matter the auxiliary proof is. It loses 100% correctness. Sometimes it will accept non-solution, but it gains the locality in the sense that it only queries a constant number of positions. The good thing is that constructing a PCP verifier is equivalent to establishing the hardness of approximating two CSPs. This procedure is also known as label coverization. And for label coverization, we just we just construct a bipartite two CSP instance. In the left side, each variable stands for a randomness, and for the right side, each variable stands for a position in the proof. And we expect that each variable in the left side is the query result under the randomness I, and for the right side, the value is just the value in the proof. And if the CSP instance is satisfiable, then we can use the properties of the PCP verifier and fill in the proof with a corresponding value. And we can say that because the verifier always accepts with probability 1, we can see that the CSP instance is always satisfied. And if the CSP has no solution, which means that every assignment will be incorrect. So no matter how we choose the auxiliary proof, the verifier will accept with 0.99 probability. And in this case, we can see that the CSP instance violates at least maybe 1% over Q constraints. So in the parameterized, we can also design the parameterized version of the PCP verifier, where we further need to make sure that the length of the proof pi and the randomness R is parameterized and is independent with the alphabet sigma. So how to design parameterized PCP verifier for vector value CSP? Our key idea is that since there's only parallel constraints and linear constraints, we can tackle them separately and then finally combine these two verifiers using the standard techniques in PCP of proximity. So for parallel parts, recall that if every constraint is parallel, so the CSP would be essentially layer by layer, and it is the same CSP across all layers. So the verification of each layer is the standard PCP theorem. So we can design a standard PCP verifier for each layer. And to verify all layers, we just run the PCP verifier for the single layer simultaneously on all layers. And we can construct the verifier for parallel parts. And for linear parts, the key idea is just this is a linear system, and we can generalize the Hadamard code to vector space and can verify this case. Then finally, we combine these two verifiers using standard PCP of proximity. As a result, we can reduce a CSP instance to a gap instance where the number of variables becomes 2 to the k squared, because we need to reformulate the lower bound using the parameter after reduction. So this gives the fk times n to the omega square root of k, log square root of k lower bound for constant approximating to CSP. Okay, this is good, but the running time is still far from being optimal. So so there's some subsequent work focusing on producing some short PCPs to get an optimal running time lower bound. And the state of the art is amplification-based approach, which is introduced by BKM25. So the basic, it also follows a similar workflow, but for the PCP verifier, it uses the verifier in BS28. The result of BS28 will give a gap instance with almost linear parameter blow-up. However, the soundness is, it only creates a little gap here, but the soundness is also very close to 1. So then, to get a constant inapproximability, it applies the gap amplification based on high-dimensional expanders. And finally, it gets the constant inapproximability with only almost linear parameterized blow-up. So the final result will assume ETH, we can obtain almost optimal lower bound for constantly approximating to CSP. And by slightly modify the proof of DM19, we can get the FPT lower bound for almost optimal inapproximability to CSPs. This is almost optimal because we can easily approximate parameterize the two CSPs with ratio 2 over k, and the ratio is k to the little 1 over k, which is almost optimal. And I also want to say that we have an alternative approach based on algebraic constructions of PCP, but this is more involved and it gets slightly worse lower bound, so I will not introduce it here. Okay, that's all. Thank you for your attention.
No questions? Do you think it can be pushed all the way to get optimal? The running time, like the polylog k can be removed, or you think it is an upper bound?
I think this is a very hard problem, and currently we don't know how to do. Maybe I think this problem is as hard as establishing a linear sized PCP. Yeah.
And suppose you had a linear sized PCP, then?
Yeah, I think so. Maybe we can try to adapt linear sized PCP to this parallel case, and then we can also get the optimal lower bound, fk to the n over k.
Thank you.